Hey everyone! Today I've put together a few circuits that look unusual at first glance, but they are completely real, fully functional, and surprisingly simple. These are proper weekend builds, minimal parts, easy setup, and nothing exotic. As always, we'll first understand how each circuit works, and then we'll build and test them. This is Mattino. Let's begin. How do you measure an LED's resistance? You don't. You use the diode mode on your multimeter. But here's an even better question. How do you measure voltage an LED generates? Oh yes, it can. Structurally, an LED is just a diode with a transparent package. That means light can reach the junction. And when photons hit a p-n junction, they generate charge carriers. In other words, the LED can act as a photodiode. This effect was documented back in the 1960s by an American engineer, Forrest Mims. Depending on the specific LED, you can measure up to about 2 volts under strong illumination. Even more interesting, an LED is sensitive mainly to wavelengths in its own emission spectrum and shorter. That means a red LED won't react much to red light, but it will respond to blue or white light. So by choosing the LED type, you can build a crude but selective white sensor. Let's use that property to build a simple automatic light switch. Logic is straightforward. Bright, lights off. Dark, lights on. But we have a problem. The current produced by the LED in sensor mode is extremely small, too small to drive anything directly. So instead of current control, we use voltage control, a MOSFET. MOSFET's gate draws almost no current, so even tiny voltage shifts are enough. Notice something important. The LED is connected anode to the ground. In photodiode mode, it generates voltage in its normal polarity. An automatic light switch uses reverse logic, so the LED must shut the MOSFET off when illuminated. So we use its cathode to create the negative gate bias. Now let's decide on the value of the resistor. It must provide enough current to turn the MOSFET on. At the same time, its value must be large enough for the photodiode to be able to pull the MOSFET's gate low. 1 nega. Illumination changes the gate voltage by only about 300 millivolts. That's not enough. Gate voltage too high. And at 4.7 megohms, the difference becomes significant. The voltage corresponding to the dark state is a bit lower than expected, but it will suffice. The load is a 12-volt LED strip, and it looks like it's working. In a real design with increased sensitivity, using a transistor stage, or ideally a comparator. But the core principle is demonstrated. An LED can be both emitter and sensor. SCRs, also called thyristors, are often forgotten today, and mostly replaced by MOSFETs. The reason is simple. They are easy to turn on, but hard to turn off. One must interrupt the current to shut off a thyristor. But that very property allows an extremely simple relaxation oscillator. Here's the principle. When the thyristor is off, capacitor starts charging through resistor R1, which makes voltage at point A gradually rise. That voltage also feeds the gate through R2. The SCR remains off while the voltage is below its breakout voltage. Once the breakover voltage is reached, the thyristor suddenly turns on. Point A collapses towards zero, and capacitor discharges through the SCR and the speaker. This produces a sharp current pulse and creates an audible click in the speaker. As the capacitor is discharged, the current flowing through the SCR drops significantly. Once it drops below its holding current, the SCR shuts off. Then the cycle repeats. I build the oscillator using a TYN412. For audible confirmation, I use a small PC speaker. Frequency depends on supply voltage and component values. And here's the beauty of it. If you replace the speaker with a load, the generator can directly power it. In the simplest form, it's literally a 3-component oscillator. That's hard to beat. What do you think this circuit does? A capacitor in series suggests AC must be fed to it. But the diode stage does not look exactly like a rectifier. This is a simple step-up circuit that does not use a transformer or a choke. It's called the voltage doubler. Here's how it works. Let's assume that at a certain AC half cycle, positive voltage arrives at terminal B, and a negative voltage at terminal A. In this case, diode D2 will be reverse biased, and no voltage will reach the load or capacitor C2. The current, meanwhile, will flow along this path through diode D1 and capacitor C1, and the capacitor will charge to the corresponding polarity. Now let's assume that the next half wave begins, and the input polarity reverses. C1 is already charged, so when the positive voltage arrives at terminal A, it connects to its negatively charged terminal. The current flow direction in this case coincides with the forward bias of diode D2, and the current follows the longer loop, supplying the load. Since the circuit's power supply and capacitor C1 are now connected in series, their voltages add up, and capacitor C2 receives a voltage equal to twice the supply voltage. The circuit is scalable. Add more diode capacitor stages, and you further increase the voltage. It's simple, elegant, and widely used when high voltage but low current is required. It's often used in audio equipment, for example, studio microphone phantom power circuits, because unlike a transformer, it can step up voltage without creating magnetic noise. Now let's build a doubler energized by a 555 timer. We will use the same diode capacitor stage, but the connection scheme will be slightly different. The reason is because the 555 does not output true AC. Its lower half wave is not negative relative to the supply. It's merely a square wave oscillating between 0 volts and power supply voltage. So we use a capacitor in series, the C4. Here's how this circuit works. When the 555's pin 3 is low, diode D3 conducts, and capacitor C4 charges. C3 also charges through diode D4, but so far to the supply voltage only. Then pin 3 goes high, which roughly equals the supply voltage. Since the C4 is already charged, its voltage is now added to the potential of pin 3, yielding double the supply voltage at point A. Diode D4 turns on, and current flows to capacitor C3 and the load. D3 at this point remains reverse biased, since the potential at point A is higher than the potential of the positive rail of the power supply. The result is roughly twice the supply voltage. Circuits like this one are ideal where efficiency and power are not critical, but simplicity is. In a real world, ICs like TC1044 are often used to drive charge pump circuits. The 1044 is a highly efficient monolithic CMOS switched capacitor voltage converter, providing full 1.5 volt to 9 volt supply operation. Here's another one for you to check out. At first glance, this circuit looks absurd. Input and output capacitor couplers suggest it's an AC circuit. However, the diode can pass only one half wave. So what is this? A signal distortion circuit? Nope. This is actually an analog switch controlled by a logic signal. When the control line is low, the diode is reverse biased. No signal passes. When control is high, the diode is forward biased. The analog signal passes in both directions without any distortion. There is an important condition, however. The signal amplitude must remain below the diode's forward drop. Otherwise, signal will be rectified, that is, distorted. But if necessary, multiple diodes can be used in series. That would allow to pass higher voltages without distortion. Let's test it with a sine wave from an AD9850 DDS generator. Let me attach the bench PSU set to 5 volts to the control input. Control off, no output. PSU is now on, control on. Clean sine wave appears. The concept works cleanly and predictably. Now something even more interesting. What does the Q1 do in this circuit exactly? Well, did you know that if you reverse bias the emitter-base junction of an NPN transistor, it exhibits the so-called avalanche breakdown, process similar to what's happening in a Zener diode. That means it can actually act like a Zener diode in a real circuit. The breakdown voltage, however, varies between transistor models and even between individual samples. Let us test several transistors. We will use a classic simple rig consisting of a DC supply, a 1K resistor, and a voltmeter to measure voltage across the Zener. Actually, any decent bench power supply can do this. I am using the DBS 5020. It allows you to limit current and also has a built-in voltmeter. One important thing to remember when using it: bench PSUs have a large capacitor at the output stage. So never attach a Zener diode while the output is enabled, unless you want to burn it. 2N2222 yields around 9 to 10 volts. Two N3904 around 12 volts. Others vary. So let us build a simple parametric stabilizer. 2N2222 as the breakdown reference, that is Zener replacement. DC548 as emitter follower. The measured drop at the 2222 is 9.2 volts. But the transistor will also introduce a voltage drop of around 0.7 volts. That means we can expect to get about 8.5 volts at the output. Oh, let's check it out. Input 11 volts, output about 8.4 volts. Now I increase input to 21 volts. Output barely changes. the voltage is effectively stabilized. For mass production, no. For a hobbyist emergency solution, absolutely. LEDs can also act as voltage references, but in normal, forward bias. White LEDs give higher voltage route, red give lower, and they also glow while doing it. Is the goal? Semiconductors didn't always exist. So what did engineers use before they came around? The so-called magnetic amplifiers, also called saturable reactors. Such circuits use a control current to saturate a magnetic core. The operating principle of the device is shown in the figure. Electrically, it's virtually identical to a regular transformer with 3 windings. The load to be switched, here an incandescent lamp, is connected in series with the 2 primary or operating windings. Note that these windings make a subtracting, also called series opposing connection. This is necessary to prevent the generation of an EMF in the control winding. The combined magnetic field they create will be 0, and the device will not behave like a conventional transformer. The control current is supplied to the secondary or control winding. The primary operating winding contains relatively few turns. In its initial passive state, the magnetic flux it generates is insufficient to saturate the core. The load, the bulb, is thus de-energized, since most of the supply voltage drops across the reactance of the primary winding. The secondary control winding, however, contains a large number of turns. If current is passed through it, a magnetic field is generated, and the magnetic core saturates. As a result, the reactance of the primary winding drops sharply, approaching its resistive value. Current flows through it, and the load is energized. The circuit can also operate in analog mode, meaning the current passing through the load can be proportional to the control current. So it's essentially a transistor made of copper and iron. Old technology, but beautiful physics. Let's demonstrate the effect with a simple transformer and a lamp load. As you may have noted, this explanation deals with the concept of reactance. Reactance, if put simply, is a special form of resistance, exhibited by inductors and capacitors in response to alternating current, AC. Reactance, just like resistance, is measured in ohms, but denoted with Latin letter X. However, unlike resistance, reactance does not dissipate energy as heat. So if we're dealing with an inductor, it basically has 2 types of resistance. First, resistive resistance, the one you can measure with a multimeter. Second, reactive resistance, the one it effectively demonstrates when AC is passed through it. Finally, the most exotic one. What the hell is that? Well, if you reverse connect an NPN transistor in a specific configuration, it can enter a certain region where increasing voltage results in decreasing current. And this nonlinear behavior is called negative resistance, which allows oscillation without inductors. Here is how the circuit operates. When power is applied, the current quickly rises to a certain value defined by resistors R1 and R2. When the voltage between the collector and emitter reaches U0, the transistor shifts into the negative resistance region, so the current starts to decrease and falls until the voltage reaches U1. A further increase in voltage shifts the transistor into the positive resistance region, resulting in increase of current. This causes the voltage across the transistor to drop again, while the voltage across the resistors rises. The principle underlying this generator is called negative differential resistance, or the tunnel effect. It was first discovered by Japanese physicist Lewel Isaki, who was awarded the Nobel Prize in 1973 for this discovery. So, a semiconductor diode exhibiting the tunnel effect is called an Isaki diode, or tunnel diode. Because reverse breakdown voltage is not a standard characteristic of a transistor, when building the generator, we must determine it experimentally. Thus, the potentiometer in the circuit. It sets the transistor's operating current, not the frequency. But note, only ambient devices show this effect. Also, not every sample will work, and supply voltage must be experimentally adjusted. I used a 2N2222, and the circuit oscillated immediately. If we increase capacitance, oscillation frequency drops, and vice versa. Waveform shape reflects fast discharge and slower charge. Pure semiconductor physics. No tricks. That's all for today. Links to components you can find in the description. If you enjoyed this video, please share, like, and subscribe. And if you'd like to support the channel, please also use the links in the description. All donations go directly into new components and lab equipment for future projects. This was Mattino. Be good.